All right, so welcome back, everybody. This is our last Thursday. Two main topics for today. Ted's gonna tell us a little bit more about the neuroscience and the theory of 2488, one of the models we discussed yesterday from the last class from Model DB. And then we're going to talk a little bit about HOC, because one of the things that we discovered as we were doing the Model DB exercise is that some of the models, in fact, many of the models in Model DB are not written in Python. They're written in an older language. And what can we do? And what do we need to know in order to be able to interact with them successfully? The key thing, I'll go ahead and tell you the big spoiler right now. You don't have to rewrite everything. You don't have to switch to it. You're able to take advantage of all the other stuff as is, but more on that later. So, Ted, do you want to take it away?
Okay, sure. Um, let's talk about this particular model. One very important thing about the this particular model entry, which is again 2488, and let me share my screen here so we can have a look at it. Let's see. Ta-da! Participants, share screen, advanced. There we go. Portion of screen, share. Great. Okay, so this is a model which came along at an important time in computational neuroscience. And I don't know how many of you are aware of the history of interest in activity, spontaneous activity by nerve cells and their patterns of action. That is, what kind of spiking patterns they have. And one of the theories that was very common in the starting in the 70s and going into the 80s, 90s, et cetera, was the idea that there's something special about whether a cell fires tonically when it's subjected to a steady injected current or whether it fires in bursts. And the special thing was often attributed to be that cells that would fire in bursts when you inject a steady depolarizing current did so because they had some special ionic current that other cells didn't have. So there was a lot of interest in post-spike hyperpolarization currents, which are mostly calcium-activated potassium conductances. And the notion was, well, you could get, if you fired one spike, you'd get a bit of a post-spike hyperpolarization. And if you had two spikes that were close together in time, there'd be a bigger post-spike hyperpolarization. And if you had enough spikes in a burst of, if the cell fired at a high enough spiking rate, you get such a big post-spike hyperpolarization that the cell would then engage in what's called rebound excitation after it had recovered from the hyperpolarization. Now, the mechanism of rebound spiking is any cell that has a delayed rectifier potassium current and a depolarization inactivating sodium current can do some rebound spiking. Essentially, what's going on is when the cell is at rest under ordinary conditions, sodium conductances are maybe 30% inactivated because of the H term in the HM cubed expression that determines the net gating of sodium channels, of typical spike sodium channels. And that potassium conductance, the delayed rectifier potassium conductance, was somewhat activated, like 10–20% activated already. And the net effect of that would be that the cell was less excitable than it might otherwise be. If you could hyperpolarize the cell and hold it maybe 5 or 10 microvolts or 15 microvolts hyperpolarized for maybe 10 seconds or so, or 5 seconds or so, what would happen is sodium inactivation would go away so that a larger fraction of the sodium channels would be available to activate, and potassium activation would go away so that there was less background potassium conductance. So then if you suddenly stopped your hyperpolarizing injected current, the cell would not merely return to resting potential, but could actually overshoot in the depolarizing direction, and if it overshot enough, you could get a spike out of it. Now you can see this in a single compartment Hodgkin-Huxley model. You can see this in many models of cells with other kinds of ion channels in them that have other kinds of dynamics. But basically, it's a widespread phenomenon. So the idea was that there was something special going on with that made bursting cells tend to want to burst. And again, this was often attributed to having a special current. Usually it was some kind of a special potassium current. Maybe it was a combination of a special calcium current plus a calcium activated potassium current. And maybe it was a persistent sodium current, or maybe some special calcium current that would have a low threshold and be activated readily by some kind of like a rebound spiking phenomenon. Or it could even be like an H current, okay, which is channels that tend to deactivate when depolarized and activate when hyperpolarized. And so all these fanciful notions came about as to what made cells fire in bursts as opposed to tonic firing. So it was typical, what you'd think if you thought that genotype was phenotype. And of course, people who could spell genes were enamored of this because that meant they could analyze, the genetic expression in a cell, and they could tell you what that cell would do, and they wouldn't have to do any of that messy electrophysiology that involves poking cells with electrodes and all that stuff. Well, Manin and Sinofsky were publishing this article at a time when that kind of thinking was still very prevalent. And what they showed was that it was wrong, that it wasn't the genotype of the cell that determined, it wasn't the channels that the cell expressed that determined its dynamics. It was also where the channels are expressed. And so they structured their models, they deliberately structured their models to separate the spike generating currents, the fast activating and inactivating currents, from the slower, the channels that have slower dynamics, which they put out in the dendrites. They put the spike generating currents in the cell body and axon, and they put the slower dynamic currents out in the dendrites. And the fact that spread of charge between the dendrites and the cell body takes time, this introduces phase shifts that allow oscillations to occur. So when you're decoupling the currents that are responsible for the prolonged hyperpolarizing phase from the currents that are responsible for generating the spikes, you could get bursting activity. So it's not just what channels are expressed, it's also where they are in space and what their characteristics are in time. And space and time are things that most people who come from a biochemical background don't even think about. In fact, most biologists don't even think about the importance of space and time in neural function. But these are critically important. Okay, so this was an excellent paper that should be known, should be taught to, should be exposed to anybody who's going to do genomics. Otherwise, they fall into the old patterns of thinking. And in fact, the old patterns of thinking are still around. I've been to a couple of workshops recently at a very large, very well-funded institution whose name you would know immediately, and you could probably guess. They have a lot of people doing some really nice uh, single cell expression analysis, and they largely think that the genotype is the phenotype. Okay, well, anyway, as nice as the paper is from the standpoint of the points that it made, it has some traps for the unwary. It's a beautiful paper in terms of the way it's written, in the way it's been conceptualized, in the analysis that was applied. And the people who implemented were smart people. There's no question that everybody knows Terry Sinofsky, and Terry's a genius, absolutely. And those of you who don't know Zach Manin, he's not doing that much in the way of computational modeling anymore, but he's also extremely smart. And they were doing this at a time, they were doing this modeling at a time when NEURON was relatively new on the scene. And there were relatively few papers that used NEURON, and most people who were modeling were using homebrew code written in BASIC, God forbid, or Fortran, or C, or, I don't know, something else, whatever else. One guy wrote something in Lisp that he uses, and he still uses it today. So they wrote their paper, they made their code available as soon as we had, I mean, they made it available before there was a model DB, and that was generous of them to do that. And as good as that was, there are some problems. And where do the problems arise? Well, the problems arise from the fact that if we look here, and you see the README, you'll see a discussion of part of this. Where is the discussion? No, it's not in here. It's in some of the mod files. So, for example, the sodium conductance, and you all last week considered this fact that the model is based on channel descriptions that were originally developed for cells that operated at a lower temperature. And what Terry and Zach wanted to do was make something that would work at body temperature, close to the body temperature of a rat. So they had to come up with appropriate dynamics, and they had to come up, it turned out they had to also come up with appropriate channel densities. So they could make the channels operate fast, but when they used the original channel densities, there just wasn't enough oomph there. There wasn't enough, I mean, the sodium channels activated and then inactivated so quickly that there was never quite enough sodium current to get the cell to do the accelerating part of the upward stroke of the spike. And similarly, there were problems with the potassium channel. And so what they had to do is they had to adjust channel density. Well, the way they did it was to apply a factor, a correction factor, a scaling factor to their channel to equations. And you'll see that what they did here is in the breakpoint block. Here's the breakpoint block, and you'll see that the net sodium conductance is not just the product of the channel density G bar times m cubed times h, but they threw in this additional scale factor, which is temperature dependent. Okay, and this is a hack, and it does work. It made their model able to spike, but it's a particularly pernicious hack. It worked fine for them. They knew what they did. They were never going to misuse this code because they know exactly what they did. And they knew exactly why they did it. But anybody who picks up this bag of mod files and goes off and gaily tries to reuse it for their own purposes is not going to know that this is going on. In fact, even if you use all of these marvelous introspection capabilities that we have with Python, you're not going to discover it because the correction factor is applied in such a way you can't introspect this. Neuron doesn't expect there to be any such thing in a Hodgkin-Huxley style formulation of a model. Okay, it'll discover the ionic conductance for you, and you can discover the values of the gating variables, the gating states, but you're not going to be able to discover what this is used for unless you look inside the model. Let's take a look at the neuron block. Here's the neuron block. Do you even see T-adjust in that neuron block? TADJ? No, it's not in the neuron block. So is it a parameter? Is it listed as a parameter? Well, because why do I ask that? The reason I ask that is because parameters are automatically visible to HOC and to Python as global variables, okay? And you can discover the global variables that are associated with any particular ion channel mechanisms. Well, T-adjust isn't even a parameter. So it is hidden totally from the interpreters. Okay? So somebody who knows all about using Neuron's methods for introspection of models is still not going to discover this T-adjust thing. It's called an assigned variable, and assigned variables aren't visible outside of the model unless you declare them in the neuron block. We don't see it here. Okay, so you're not unless you look at the source code, you're not even going to know it's there. You're not even going to suspect it's there. So, although it worked well for the purposes for which it was used, wait a second, it is listed as a T-adjust. It is listed as a global, but you're still not going to know what it's used for unless you read the darn source code and then discover this and then have the insight that, hey, they're tacitly increasing the effective channel density. So people don't like to look at end model source code. It seems arbitrary. It seems confusing. It would be much better if there was some other way to specify channel properties, say with Python statements that are nicely documented and that we can read about and we can play with. But there it is. There's a lot of channels that are specified with end model code, and it never hurts to look at the source code. If I picked up a mod file and I found this kind of stuff going on in it, where an effective channel density is being calculated, I would not use that mod file. I don't want to propagate that in the field. I don't want to spread use of this style of achieving excitability of a cell, because people expect that a Hodgkin-Huxley style formulation is going to be a Hodgkin-Huxley style formulation. Okay, they expect it to contain ODEs that follow the typical alpha, beta, or tau and steady state value pattern, or a kinetic scheme that follows the typical Markov style specification of states and transition rates. They're not going to expect this kind of thing. So violate violate what are generally accepted as standards at the risk of causing real headaches for people who then later use your code. I'm not saying this should be removed from Model DB, but I am saying that it's an example of a dirty hack that works, but you should never use it. Okay?
So Ted,
Yeah.
if I may, so what, I mean, so it just seems like TADJ is just a, I mean, given that they're looking at one specific temperature, it's TADJ is just a constant. Why not just change what G bar is?
Precisely. Why wouldn't they just have calculated what should be and then bury it in there as a magic number? I don't know why. Maybe they thought it was a strategy that could scale because most of the channel descriptions that were out there were either from invertebrate cells based on experiments in invertebrate cells, or they were from a handful of studies on vertebrate slice preps done at room temperature. So I can't read their minds. I don't know why they did this. It's clever, but think back to your own experience in programming and think of the times when you've done clever things when you thought later on, I don't know if I like that. Let me go back and do it a different way. It'll be just easier for me to maintain in the future, etc. Okay, so yeah, it would have been perfectly fine for them to have a comment in the code that said, the original model had a G bar of such and such, but in order to get spiking at higher temperatures, we have scaled this by a factor thus and so. And that's why the parameter value is now X instead of Y. That would have been fine. That would have been perfect. Okay, so now that we've taken care of that, which is, and again, you have to, if you're borrowing other people's code, you do have to look at the end model code, and if you see stuff that looks odd to you, then ask questions. And it may look odd to us too, and nobody is born knowing how to write Python, although I know some people about whom I kind of wonder. And certainly nobody is born knowing how to write end model. And there's a heck of a lot larger body of information about how to write Python than there is about writing end model code. So if you have questions about somebody's end model code, ask. It's perfectly fine. We'd be glad to help. We'd like the source code in ModelDB to be exemplary in a good way. Okay. All right. We'd like to
That's
help
a
you.
question, by the way.
Yeah. Is there a question? Ben?
Hi there. I just had a random idea.
Does this happen often?
Has anyone been tempted to design some routine that just tries to set a parameter, say, set a parameter in Python, try to implement it in the model, and then pull the parameter back out of NEURON just to make sure that everything is set to what I think it is?
I don't know, but you certainly can try that. But you can certainly, with well-written end model code, you can very easily with Python or HOC discover what parameter values are anyway.
Yeah, I feel like what I was saying is kind of, it sounds nice, but it doesn't, I don't think it's practical to, you basically have to have the computer smart enough that it can program itself to do that job for you.
Well, yeah, well, computers are pretty fast, but they're not that smart. They can, if I do something stupid, then with a computer, I can make many stupid things happen in a blink of an eye. And I have. Anyway, so let's take another look at something else.
I just want to point out, just also for the record, right? Like if you set a value, ultimately you're going to come back and you say, hey, computer, what's G bar? It'll tell you whatever you set it for. It won't do the T adjust because it's not changing the value of G bar. It's just using it in a way that's slightly different than you'd expect because it's scaling it first.
Precisely. Precisely. Yeah. So again, always look at the end model code and try to write your code in a way that doesn't break introspection. And it's not hard. It's not hard. Um, but it's also when people have the freedom to write whatever source code they want, it's also quite not hard to write code that does weird things and still works under certain, under careful conditions. This works fine, but just don't do it this way. Okay, let's see. Spine scaling. Let's talk about spines next. That's the other thing that this paper does. Um, does anybody know anything about the electrical properties of the membrane that's on spines? I mean, all spines have membrane, right? And we assume that it has at least membrane capacitance, and it probably has some ion channels. Does anybody know anything about the density of spines? How abundant are spines on cells that have spines? There are no anatomists among us?
I guess it depends on the type of the cell.
Yeah. So if it's a pyramidal cell, tell me
It's 1 per micron in
1 per
C1
micron
pyramidal.
length,
Yes,
or is it
I
one
think.
per, or is it 1 per micron square area, square micron surface area?
Uh, well, it's pretty late where I am, so I won't be
Oh,
able
yes,
to
yes,
answer.
yes. Yes, well, okay. Um,
Sorry.
yeah, well, your own spines are still working even if it's late, but thank you for participating. I appreciate it. Yeah, it's generally the number that people use is about 1 per micron length of neurite. Now, I think that's probably the wrong way to specify it. I think a better measure of spine density would be per square micron of surface area. Why do I say that? Because large diameter dendrites have a lot more surface area for there to be spines attached to. And is it true that a primary apical dendrite that's say 4 or 5 microns in diameter really only has one spine per micron length? That doesn't seem quite right. Now, what about the cell body? The cell body's got a lot of spines attached to it. It has, especially, well, it can. Okay, but there are two things about spines, and we really don't know what the density parameter is. We kind of accept 1 micron, one spine per micron length of neurite as a rule of thumb. But we all kind of understand that actually it probably varies at different points in the cell. So the cell body may not have um, a spine per square micron, but it might have more than one spine per micron length. Just don't know. Make friends with an anatomist and ask them if they can tell you. Um, how do you take into account the surface area that these spines add? Roughly, what is the amount of surface area that a spine adds to a cell? About a square micron, somewhere around 0.8 to 1 square micron, unless it's some kind of a giant spine in which, like the thorny excrescences on the proximal dendrites of CA3 pyramidal cells, which may add many, many square microns of surface area. So in a cell that's got a spine per micron length and may have 5 to 10,000 total lengths of neurites, not counting the axon, that's up to 5,000 square microns of surface area. distributed all over the cell. How do we take that into account in a model? What we get from our morphology studies, what we typically get from neurolucidity reconstructions, is we typically get diameters and lengths, okay? We may get indices, markers that say, well, we saw spines here, 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 and there. But we don't know where all the spines are because sometimes a spine is lying on top of a dendrite or behind a dendrite, either in front of the dendrite or behind the dendrite, so it's kind of hidden. You can't resolve it. But even so, we for spiny cells, we have to have some way of adding the surface area to the cell. Well, there's a couple of ways to do it. If you assume that spine density is best specified in spines per unit area of the cell, then you can say, well, if we know that a spine has an area of 1 square micron and spines occur at a density of 1 spine per square micron, that means for every square micron of surface area of the cell, we have an extra square micron of surface area added by the spines. And all we have to do is figure out a way to use that factor in our models. Well, in NEURON, it's real easy to do that because membrane capacitance is specified in terms of microfarads per square centimeter. So if we think that our cell has, say, 50% more surface area because of spines, what we do is we simply multiply specific membrane capacitance by 1.5 in our model. And that automatically incorporates the electrical effect of those extra spines. How can I say that? Well, because there's very little surface area, and there's also a resistance in the spine neck that separates the head of the spine from the dendrite itself. But if you work out the equivalent electrical circuit, that resistor of that neck is very small compared to the resistance of the spine membrane. So effectively, the spine is closely coupled. The spine surface area is effectively closely coupled to the surface area of the section that it's attached to. So you can do this. You can do the same kind of compensation for all of your channel densities. If you assume that leak channels are ubiquitous, then we just multiply our channel density for the leak by 1 plus what we think the spines add in terms of fractional surface area. So if spines are adding 50%, we would increase our G leak by multiplying that by 1.5. We do the same thing for voltage gated channels, etc. Now clearly, if you were this would not be the way you would proceed if you were studying, say, the properties of channels in spine membranes per se. Like if you had evidence for different channel densities in spines, you would do something different about how you would take those into account. But unless there's some reason to do that, the typical way is to multiply all channel densities by whatever the area factor is and multiply all membrane capacitances by whatever the area factor is, okay? So it's 1 plus whatever the factor is that spines add. That's the easy way to do it. And the nice thing about that is it ends up with your cells look normal. You're not doing anything to the shape of the cell. And it works economically. It doesn't do anything to the computational burden. There was a time, however, There was a time, however, when there were discussions about the best way to take spine surface area into effect. And I'm looking here in one of the files here. The one is called Demo Fig 1, and I suspect the same code is in Demo Fig 2. Here we are, spines. Now, we get into Jack and Jack Noble and Chen, who were outstanding computational neuroscientists, and I think they're retired if they're still alive. I don't know. I think the Chen is now not alive anymore, but I don't know about the others. But these guys were extremely smart and very sophisticated mathematically, and they wrote some marvelous papers and some excellent, they had at least one excellent book about electrical signaling in neurons. And they were very clever. And Guy Major did a postdoc with them in the early 90s. And they figured out a clever way to take spine surface area into effect. And what they did was they didn't do the channel density multiplication that I talked about, or the specific membrane capacitance multiplication that I talked about. They weren't particularly interested in looking at pretty pictures of cells. They wanted mathematically nice results. So what they did is they figured out that they could take the spine surface area into account by increasing the length and the diameter of every section by factors, by a factor, a correction factor. And what was the value of their correction factor? Their value of their correction factor is given by this formula, F equals L times yada, yada, yada. A is the local surface area, okay? And the thing that they did was they stretched compartments, okay? They made them longer, and this is now HOC code. So this is actually changing the model specification. The length of every section is changed, and they did this unfortunate thing of iterating over all nodes, which messed up their correction for their last node too. But don't even do this at all. Don't fix that and reuse this code at all. Why is that? Because it makes your cell look weird. That's one reason. It actually changes the shape of the cell. Okay? It does in fact produce something that is electrically equivalent to adding additional specific membrane capacitance and ion channel density the way I talked about with simple multiplication of those parameters. But it's weird. And your figures will be weird. And your space plots will be weird, because if you look at the variation of membrane potential along a path from the cell body out to some distal termination of some apical branch, all the path lengths are going to be non-anatomical. They will not be the original distances from the cell body. Okay? This is bizarre. It does work mathematically, but no, don't do it. I mean, this is the only model, I think, in which I've seen this done. I don't know if Mena and Sanofsky did this in other models of theirs, but watch out if you use if you reuse any of their code, watch out if they take spines into account using a similar strategy of stretching the length of the sections and increasing the diameters of the sections. Okay, and that is just it's just unfortunate. Oh, and when you get done with that, I'll tell you another reason why it's not a good thing. Suppose you're going to use this model cell as an element in a neural network like a cortex, and let's say you're going to wire your cortex up based upon the anatomical relationship between where branches are and where axons are. And let's say that before you do your wiring, you build your models, you build your model cells, and then you stretch them according to this algorithm, completely distorting their shapes. And then you put your you try to see where the axons are close to the dendrites, and it has no relationship to reality at all. Okay, so it's a bad practice, and you do have to look. You do have to look at model source code sometime, and that's why. And you can't use. You don't just reuse code that you find. Be sure you look at it. And if you see weird stuff and you're not sure what to make of it, it may be best to not use it.
So Ted, do you happen to
And
know, do they address their strategies in the paper?
no, not really. They might mention that they compensated for spine area using the folding factor. I have these references myself. If you want to look them up and read them to understand them, do so, but take along the lesson that although it's mathematically very clever and it does work, you're not going to want to do that. Okay, I would not say that this code is code that would set back the field, although maybe it is why we haven't figured out how the brain works. I don't know. Maybe we should look into that. But snarky comments aside.
And so again, the way that you would address this now would just be to have a scale factor on the conductances?
Yeah, I would simply say, well, let's assume that spines add this much additional percentage surface area to our neurites. And if that isn't quite what you want, if you think that it's one spine per unit length, then calculate the total. You have the total length of your dendrite of each section. You have the total length of each section, and you multiply that by 1 micron, and that tells you how many microns of surface area to add to your section. You can calculate the surface area of the section. That's real easy, and you can then take the ratio of section area plus spine area over section area. And the numerical value of that is the scale factor you would use to multiply CM and channel densities.
I was going to say, I was going to point out capacitance also changes.
Yeah, absolutely. It sure does. Yeah, capacitance. Oh, the other thing about this weird stretching of lengths and diameters is that it also destroys air volume. So if you're interested in calcium accumulation in the cell, or potassium accumulation outside of the cell, or release of calcium from intracellular stores, you've totally destroyed the volumes of distribution of all of these things, and then you're going to use something as elegant as RxD to help you figure out what's going on in the cell. I don't think that's bad. Don't do it in the first place. Okay. All right, I'll get off my soapbox now because Robert is going to tell you about the things where to find out what you need to know and how to go about thinking about looking at HOC code, because you may have to actually look at some just to make sure you're not stepping in some booby traps. Okay. Are there questions about anything I've talked about so far? Not yet? Okay, good. Let me unshare.
All right, thanks, Ted, for that discussion. There's a couple of things that actually came up that I do want to highlight just for the just for the record here. So let me see. So there was a statement about people not being born knowing how to write in modal. I don't know what that's about. But no, so one of the things you can, so in modal is but one way of expressing channel kinetics in Neuron. In practice, it's the one that you're going to come across, especially if you're looking up against whatever's in ModelDB. There are a couple of examples in ModelDB that use this thing known as the channel builder, which is gives you a graphical way of expressing channel kinetics. The other thing that I wanted to point out, though, is there is actually a way to do this in pure Python and still run at machine speed, which is to use this thing called RxD, which we haven't really talked about, more on that later. It's normally for the reaction diffusion kinetics, but fundamentally it's a Python-based way of specifying dynamics for your cell that respect, the geometry and all that jazz. And then these things get specified in Python. You can query them. You do all your regular Python introspection. They're actual Python objects, but behind the scenes, when you enter these equations, they get compiled into C code. That C code gets loaded in. This all happens in the blink of an eye. The C code is much simpler, actually, than what NModal uses, and so it's actually pretty fast, and we don't even bother. You don't see it. As somebody using Neuron, you don't have to touch it. You don't need to know that anything is actually happening behind the scenes. But it is happening behind the scenes. It is compiled into C. It does run at C, full C speed that we kind of expect. And so what I want to point out is, so here in the Neuron, sorry, I gotta zoom in over top of it. In the Neuron homepage, if you go to documentation and you look at reaction diffusion, there's this thing called Hodgkin-Huxley using RxD. And then this is an example. You can see we're setting temperatures, we're setting conductances, we're setting reversal potentials, we're calculating our various functions. We're just defining a geometry. So what's happening here, this code here is one that compares it, so it runs it twice. One of them gets the mod file, one of them gets the kinetics as specified in Python, and we validate them. And so you can declare that on the outside of the cell there's sodium and potassium, on the inside of the cell there's sodium and potassium. You can write out, hey, look, there's a sodium current that involves some conductance, V minus ENA. We'll see where this is. That conductance is a parameter times GNA bar, M cubed H, etc. And so you can do all of this. You can specify your kinetics in this way. You can record everything. And then this is a bunch of plotting. And then we compare the two different approaches, given given the same stimuli, and we see that they are functionally equivalent. So that is a thing that you can do. I don't think you'll find anybody in ModelDB that has done it that way. Honestly, the mod file syntax, even if it seems a little bit mysterious, it is fundamentally pretty closely tied to the kinetics, and it does work quite well, but you don't have to use that. One other thing that I wanted to point out, because it came up, oh, and I should say, by the way, let me do one other thing. If you want to know more about reaction diffusion, we haven't really talked about that, but Neuron supports the full, chemical dynamics inside the cell, 1D and 3D, chemical dynamics outside of the cell in 3D. So you could imagine if you have an astrocyte and glia and they interact, astrocytes and the neurons, and the astrocytes regulate extracellular potassium or something like that. You can model all of that with Neuron. And so, like I said, we obviously haven't really talked about that, but if you go to the Neuron Simulation Environments YouTube page, we actually have a video from CNS 2021, and this is also cross-posted on the CNS YouTube channel as well. You could go there if you prefer. But either way, there's a video from CNS 2021, and just over 2 minutes into it, I got Adam Newton, postdoc working with me, gives an introduction to reaction diffusion kinetics in NEURON. This is relatively brief, and it's an hour-long introduction, so but it gives you some, and he's got some examples that he works through. So you may want to check that out. And there's a whole section on the programmer's reference. If you're on Read the Docs, Read the Docs, there's a whole section on RxD tutorials. You can also go there and check them out as well. And everything that's here should have an associated. Yeah, so most of the stuff, if not all of the stuff that's here, also has an associated Google Colab link. So you could look at it, you could read the static description, or just click over into the Colab, and then you can get an interactive thing where you can mouse over it and see everything that happens and change, run it locally and change things as you wish. So I want to point that out. Does anybody have any questions on sort of alternatives to N-modal? Yeah, Ted, did you unmute?
I did, but just out of idly clicking. One of the things you might want to do is to, when you're starting out, if you need something that you don't automatically have a mod file for, again, you try to find something that somebody else wrote that doesn't look too bad and comes close to what you want. And you can often just get what you want by just making a few modifications and testing to verify that it works the way you expected. And that's one of the ways to obviate having to write all that additional boilerplate that's in the N-model file.
Absolutely. One other thing that I do want to point out, so there was this discussion about introspection. So imagine, so here I'm in Python from NEURON import H. Okay, cool. So you may have seen that there's, if I were to create a SOMA, I could create a SOMA as h.section. I'll give it a name of SOMA. And so I've been advising you to put ion channels in using h.hh.insert, and then you can do it, throw it into SOMA. You could throw it into a list of channels. I like this because I can put it, if I've identified a list of sections, like all of the apical dendrites, I can put everything, put Hodgkin-Huxley channels into the apical dendrites in one go. Cool. The other option.
In other words, you could use a list as the argument.
Absolutely. So I could just as easily have said a list of SOMA. That doesn't really do anything, but yeah.
Yeah, but if you had a list called apical dendrites or something like that, you could do that. Sure. Okay.
Yeah. So you got SOMA.WholeTree is everything that's attached to the SOMA. There's also a subtree, which is everything that, so whole tree is the entire cell, right? Everything that there's a path, every section that there's a path to get from one point to another is the whole tree, right? So if I just give you the most distal apical dendrite, whole tree is still everything that's attached to it. So I can go back, that's going to include this. If there's a path to the SOMA, so whole tree will return, the SOMA and everything. On the other hand, there's also this thing called subtree, and subtree is, so presumably there's a root, usually a root node that everything you start out is being attached to the SOMA. If you assume for the moment that that was how your cell was connected, it wouldn't have to be, but that's what import 3D will do. Then the subtree is everything starting at the current section and going out. So if I have the first apical dendrite, I could ask for that apical dendrite subtree, and then that would be by definition just the apicals and none of the basals or whatever. So yeah, so you could pass in the subtree, which is everything in that, assuming the SOMA is the root, everything at that point, that section and everything further away down that subtree, if that makes sense. So it's a great way of specifying this. There's another syntax. So we do support you've seen soma.insert h.hh. I don't particularly like this because it's just one section at a time. It's the same thing, but only one section instead of you being able to do the whole thing. But the reason that syntax exists is because in the olden days, you had to say soma.insert the string HH. Okay. And those are all equivalent. And since I'm just inserting the same thing over and over again, I'm still only have one copy because NEURON's smart enough to know that it's the same thing. But yeah, so why am I mentioning this? Why did we move from the string HH to working with h.hh as an entity itself? Well, there's two reasons. So first of all, it gives us the
Quick
ability.
question, Robert.
Yes, sir.
In the second one, because you have discussed this before as well, but I forgot to ask, in the second format, soma.insert.hh, so in that format, could one add multiple channels to soma, just like the other way around? Like in that case, you are inserting HH into different sections, but using this syntax, can several channels be added when we have multiple channels, individual channels, and not?
I mean, the short answer is no.
Okay.
You could imagine that maybe, I think it's an interesting idea. You could imagine that in some future universe, maybe we go down that road. The logistical difficulty is right now, basically soma.insert is looking for an object that has a certain, from the programming side, it's looking for objects of a certain structure, like that have certain methods that it can invoke that allows them to insert itself in there. And lists don't have that, and so it would need a special case. It would need to go back and look. But I think that's not that hard. We could do that, maybe. I'm not promising you that I will do that, but I like that idea. But yeah, so that's a good idea. It's not currently supported. We'll see. But the other advantage of this is now this makes our ion channel, so h.hh, it's a class, right? It's this own first level thing. It's a density mechanism that corresponds to the name HH. And so in particular, I could do h.hh dot and then hit tab a couple of times. And so I see that it has some methods that are associated with it, right? It's got insert, it's got uninsert. It's got code. Let's look at code. h.hh.code. Well, that's one giant string is what that is. But if I were to print it out, instead of just having it display, if I were to print it out, you see all these /n's, those become new lines, /n right there. So if I were to print that out, hey, look, it's the source code of the h.hh mechanism. And so I can always go back and I can do, I can say help of h.hh, and that's going to be, it's going to show me that initial discussion, that whatever was in that first comment of the mod file becomes the beginning of the help file, that you get on a given channel. So we do have some ability to look into these mod files. They're not completely opaque. If you have the nmodal library installed, and so if you don't, you can just get it with a pip install nmodal. I think it's going to yell at me because I already have it. Yeah, requirement already satisfied. But if you didn't already have it, you could install this thing called nmodal. It's a Python library, pip install nmodal. And so then you can take advantage of some of these other things that are there. So for example, AST is an abstract syntax tree. If you don't know what that is, don't worry too much about it. But what it does, you can see, is it gives you if I were to print it out, this is just sort of the display version. It is a structured representation of the concept, the content of the mod file. So it's translated, it's basically parsed, it's loaded in, and it's a thing that you can use. And we're experimenting with using, well, not me personally, but our colleagues are experimenting with using this for mod file translation, for example. And so we can use this. We can ask for what are the ontology IDs that are associated with this? Well, the Hodgkin-Huxley thing has various ontology identifiers. You can go look those up just online on identifier.org, for example, will tell you what each of these things stand for. So there is way. So my point is that there are ways of getting insights into the mod file, and we're doing more and more with this. There's not a whole lot that's there right now, but we are trying to add more and more methods to these density mechanisms so you can explore deeper and deeper into what's in there.
So these methods are all available regardless of how you inserted something into a section.
Yeah,
And
well, in fact, this doesn't
you don't
have
even
to be
have to
inserted
have
at all.
inserted anything, because you can discover it even before you have a section, right?
Correct.
Good. Now, question about these ontology data. As soon as that appears widely and people start looking at the source code for these things, we're going to find people modifying their end model files, and they're going to be preserving these same ontology tags, and they might have nothing to do with these at all, in fact. They might be for completely different ion channels with quite different kinetics. And yet users will, the typical thing that people do is they treat the source code as if it's some kind of holy script. Every token is sacred, and they just make some modifications and don't touch anything else. It's like they were Indiana Jones trying to steal the gold figurine without having the great ball of rock land upon them, So they're not going to change any of this stuff. We're going to end up with a bunch of stuff in ModelDB and elsewhere, which is going to have bad ontology IDs. Do we need to be doing something about that? And I've just to open a discussion that we might have ourselves later elsewhere, but just to let people know, what would you suggest that the current audience do if they do reuse code and modify things? Should they just simply say that, well, we borrowed this structure originally and it had these ontology IDs, but our resulting channel is not the same, so what should they be doing? What do you think?
So, if you're concerned about that, so we could, if you, not Ted, but just sort of the people in the audience, what are concerned about trying to identify something, one option is to just remove the ontology IDs. It will not cause a problem. They are not functionally used. They are simply they're simply there to help people. I do want to point out, though, if you do want to look up something, there's always BioPortal. It's bioportal.bioontology.org. So you can go in there. You can let's see. Is this going to actually work? I haven't actually tried this. So let's just say sodium channel. See what it does. All right, so I've searched for sodium channels. Let's see, NCIT's ontology. What do we have? So that shows up in 26 ontologies. And so here we are. Here's the identifier that's associated with this. We have a definition, ion channel with selective permeability for sodium. So let's see where this fits in. So in the hierarchy on NCIT, they don't have any subtypes for sodium channels, but they do recognize that a sodium channel is a type of ion channel, and an ion channel, well, is not an atomic concept. So you can look at this and you can get some information as to where different things relate. If you don't know about BioPortal, it's a wonderful website for identifying ontologies. You can even go ahead and like paste some text and it'll give you some suggestions as to what ontologies best capture the terms and the usage that are in there. On the model DB side, I think we can certainly make a point of trying to look at ontology identifiers as they come in to see if they make sense. I think we should. I think this is what's done with so biomodels, for example, is an SBML repository, and I think part of their curation process is making sure the ontology identifiers in SBML make sense.
Yeah, they probably have good, reasonably good ion channel ontology. Maybe not the same as the oncologist would use, but certainly if they're dealing with cells that contain all different kinds of ion channels, and I would tend to rely on theirs.
All right, does anybody have any other questions or comments that they want to raise? Because that's, I think, everything I want to say about, well, really mod file stuff and ion channel mechanisms. All right, hearing none, let me go ahead and move to today's main topic.
There's a hand.
Oh yes, sorry, go ahead.
Yes, before moving forward, I have a question. I guess we already covered this topic, but when there are the verbatim code on the source code, how we can address the issue with that? How we can? I'm just looking for more information about those verbatim codes, and
Well,
I don't know where I
oftentimes
can...
the verbatim codes aren't an issue at all. Some people have developed end model files that contain a lot of verbatim code and that they actually use for specific purposes. If it's working and you might not want to disrupt it at all. There are times though when verbatim code is almost gratuitous, and in some cases it causes problems.
So in particular, Yosef posted on Ask Tutors earlier today an example from one
Yes.
particular model.
Yeah.
What a return 0 or what?
No, it's from a model out of a lab that reuses a lot of verbatim code.
It's in the forum?
I guess it's in the Slack.
Oh, it's in the Slack. Okay.
Yeah,
I
so
guess
this
that's
is,
the reason that code is not working on the Windows.
yes, that's why it's not compiling. So basically what happened was, and I think this might be misc.mod. I don't remember which one this was. Yeah, it's misc.mod is the file in this particular case. And what happened was basically the C code that was used was that they were, inside verbatim block you can write anything, and it's entirely possible to write C code that compiles on one system but not another. And that was the case with that particular group, which happens to do most of its modeling within Linux.
So is there any way that I can make substitution on those lines and make it like can work in the Windows, or never work on Windows?
I mean, so yeah, it depends on your definition of is there any way. So the functions in misc.mod are basically entirely replaceable with Python. I mean, I know it's not a Python model, but it like you can mix and match Python and HOC, which is the language that particular model was written in. And so everything that was in misc.mod is replaceable. But I think that's the exact. And honestly, I would love to do that because this particular mod file is reused in a number of models. I've never personally gone back and tried to, that's a slightly lie. I have tried to fix it in one case. Yeah, I've never personally gone back and tried to do it, but I think it would be great if we could actually have an example that didn't have that dependency on that. But yeah. So in other words, happy to have that conversation, but it is a longer conversation, and there's no general rule. It's just swapping things, figuring out what. So basically, what happened was mis.mod was used to give define new functions that would run at C speed. It wasn't used for simulation. It wasn't used for anything. It was just, hey, I want a nice convenient function that will tell me, PWD, the current working directory. And it was done using HOC, which didn't have the ability to do this. Python's perfectly happy to just tell you the current working directory. But so mis.mod was this elaborate workaround in that particular case for answering a very simple question. It may have also been used for answering other questions, but you get the idea. Like at one point, it's like, okay, well, I know how to answer that question. Okay, let me get rid of that function. Let me get rid of that function. Again, happy to have it. Would love to have this updated. Happy to have that discussion, but yeah, it's a function by function thing.
So it seems to me that model source code that requires PWD to be executed by a call from machine language must be doing too many PWDs. I just can't imagine.
HOC doesn't have that as a
you can do, yeah, but can't you do system parens PWD
in HOC?
Yeah, doesn't that work?
I don't know.
I think it does, but
and then how would you capture the result in HOC?
Yeah, I don't even think of using PWD in my source code. I would develop my model, make sure my model works, and then if I need to do PWD or anything else, I would use Python simply to do all that administrative OS specific stuff outside of my model specification. I'm really not interested in mixing things that are model specification with things that are merely administrative, especially not specific operating system related stuff. I mean, I want code that's going to work for anybody, regardless of what OS they're using. I don't want to get calls back. Well, we tried it on a Mac OS and it didn't work, and it only works under Windows 11 and a half on alternate Tuesdays. I just don't want that.
Yeah, I mean, so all of those functions are completely, there are alternatives for everything, and that is an entirely removable file. But
somebody would have to implement and find out which ones of them it is that are critically important for this particular model. Yeah,
because that also file has functions that aren't even used in this particular model.
Are you yeah, sure.
So
I've seen the code. I've seen the code from the lab.
All right. Okay. Anything else anybody wants to raise? But I think that's an interesting. Am I sharing my screen, by the way?
Yeah. Where'd you steal all the books from?
It is a PowerPoint clip art that automatically suggested clip art because the title mentioned reading, and so the AI is like, ooh, books. And so all right, so I want to talk just a little bit about HOC. We've sort of mentioned that there's this thing that exists. It's this other programming language. It's the language that was used for this particular model that we've been sort of talking around, that was discussed on the As Tutors channel. And I think so the challenge with HOC is that it was a sort of, I don't know what to say this. It was never a widely used language. And so you had these holes. There were some functions like PWD, what's the current working directory, that were never convenient to do within a HOC, although we can imagine, and we've discussed, there might be some other workarounds for them. So it doesn't have any of the expressive power of Python, but nonetheless, it was an older language that exists. It's actually still available. You can, if you open up Visual Studio Code, a HOC file in Visual Studio Code, it'll be like, hey, it looks like you're running, Well, it looks like you're running a neuron model, and you are, but and then it'll offer to do, let you download an extension for syntax highlighting and all of that. So yeah, so it still exists. It's still out there. We've seen the models in this. The main and Sanowski model used it, and this other model that we've been talking about used it. So let's talk about it. And how do we deal with this? So where did this even come from? So this actually came from, there was a book by Cunningham and Pike. So this is Cunningham, as in the developer of one of the developers of C, Cunningham and Ritchie. As from back in 1984, they were trying to demonstrate YAC. And so sort of the modern alternative to YAC is Bison, because people are funny. But so YAC was a compiler language, and it was a language designed to specify how to build programming languages. And so they used this, and this was their sort of demo example, and it stood for higher order calculator. And then this was adopted by NEURON and a few other packages in the 80s, early 90s. There was an object-oriented extension called HOC. And this was, like I said, this was NEURON's original programming language. It existed before Python. Hundreds of neuron models in HOC from before, and honestly still after even Python support were added, are available in ModelDB. So what we need to do, we want to be able to, we may stumble across some HOC code. If you're working in a lab that's been in the field for a long time, that lab may have existing legacy code that's written in HOC. That's okay. We don't need to convert it. We don't need to start writing in HOC ourselves, but we can still, we can use it. But we can try to understand it. We can try to use it from Python, and we can use it to try and gain insights and how to write in Python. So if we see an example of something that was done in HOC, but maybe we can still get some insights to figure out what we want to do. So how do you even come across this, right? Like, we've been launching NEURON by going through Python usually, but turns out that there's actually a separate command. If you've installed NEURON, you have a command called NIV. So you may have this as a thing that you can double click on. If you're running from the terminal, just type NIV, and it's going to give you a nice little prompt. This is from a while ago, but the prompt looks the same, except the dates have been updated. So then you can exit it by pressing Control-D or typing quit. So that is perhaps one of the most important features. If you can't get out of it, you're going to have a bad time. If you use NIV, that's actually not going to load the compiled mechanism. So if any sort of special ion channels, so what you may want to do instead is to just run NEURON GUI instead of NIV. But you see here at the bottom of this, and I'll post these slides on the Slack immediately following. Yeah. Some other little minor caveats. So okay, so we can get ourselves a HOC interpreter, but what can we do with this? Well, first of all, we're going to want to be able to find documentation. So how do we even find an example of, so we've found some HOC, we're trying to make sense of it. What are we going to do? There's some function. I've never even seen this function in Python. What can I do? How do I use it? How do I find examples? So let me just show you real quick. If I'm it's back here to our example of using RxD to specify mod file, specify ion channels in Python. If I go back to read the docs, and I've looked up something, I've looked up some function that's interesting. I found, let's say, the graph class, and I'm wanting to know what this looks like. All of my codes in Python, I want to know what this looks like in HOC. You'll see that at the top of this page, right next to that convenient edit on GitHub button that I want to give a shout out to, so that if you see something in the documentation that you don't like, that you think could be clearer, that you want to add an example to, by all means, please click that edit on GitHub button and make a pull request. We would be very happy. You'd make the community a better place. But right next to that, there is a button called Switch to HOC. If you click on that link, Switch to HOC, it now changes to Switch to Python. And so we see instead, we see what's HOC syntax, and we see examples of using this in HOC. And so everything is changed and is now using this other programming language called HOC. So you're able to toggle back and forth between these various languages within the documentation. So just wanted to point that out as well. If you want to see more examples of using HOC, there was this book from 2006 called the NEURON book. So that book provides a HOC introduction. All the examples are in HOC. If you're in ModelDB and you want to find out how to do a specific function, so like, or class. So here there's a class for handling initialization, which we're going to talk more about on Tuesday, called fInitializeHandler. Well, how do I use that in HOC? Let's find the examples in ModelDB. So I can type fInitializeHandler, and then I can restrict to HOC files. And so I can restrict to HOC files by saying file : star.hoc. And that will search within HOC files and only HOC files for that term fInitializeHandler. So that's another way of getting examples to help you try and figure out, make sense of any HOC that you might come across. So let's talk syntax. So HOC is going to have a lot of the same kind of basic fundamental syntax that you'd expect from Python, right? So your code has to make choices. And in Python and HOC, the command for choice is if. It's different though, because now we have to have parentheses, and you don't have to really care about that because you're just reading it, you're not writing it. But so parentheses are required after that if statement, and set symbol is used to indicate the beginning and the ending of a block. So kind of like you'd indent in Python, anything between an open curly brace and a closed curly brace goes together. Indentation is completely at the discretion of the user. Indentation has no syntactic meaning in HOC. That means that you cannot trust the indentation. You have to look for what's the beginning and ending curly braces. Obviously, if for some reason, and I don't really recommend this, but if for some reason you do find yourself writing HOC, you are going to indent like you would indent in Python, but you cannot assume that other people have done so. There's so also the other major type, another major type of flow control is a for loop for doing things more than once. HOC does not have, in Python, you just have a list or an iterable, and you always loop through each element of the list. HOC doesn't have that concept built in, although I'll show you a workaround that you may find. And so instead in HOC, and this is definitely true in C, and this was true in C++ until, I don't know, some point within the last decade. HOC doesn't have a concept of looping over each element of the thing. You actually have to count. And so this syntax, if you see something looking like this for I = 1, 5, that means I is going to start counting at 1, and it's going to go up to 5. So it's going to go 1, 2, 3, 4, 5. Okay, and it's going to print these out and so forth. Again, you don't have to worry about this because you're writing, not reading. You're reading, not writing. But the print statement in HOC does not need parentheses, unlike the print statement in Python. The other thing, the potential gotcha to think about, you might think of this as a range statement. Okay, so it's counting from 1 to 5. However, 5 is included. It's the opposite of a range statement. So in Python, the endpoint of a range statement is not included. So then in Python, the equivalent would be for I in range parentheses 1, 6, because 6 isn't included. And so the last included value is 5. So if you're translating this in your head to Python, remember that last number is included. And if you know C style syntax, You can also find C-style things. I think that comma is supposed to be a semicolon. You know, for I equals 1, I is less than 1025, semicolon, I times equals 2, and with that would then count raising it by a factor of 2 every time. All right, so that more or less carries over from C. Again, not surprising. HOC and C share designer. Again, while statements very similar, so this pretty much, you can read this. I think it's self-explanatory how it corresponds to Python. Again, there's no colon, parentheses are required, and indentation means nothing, but curly braces do indicate the blocks. But otherwise, a while statement translates directly over into Python. We've already talked about this. In Python, indentation means something. HOC, indentation doesn't mean anything. It's just the curly braces. You can even do sort of really nasty things, and you'll find, and the only reason I'm telling you this, again, you would never be the person who does this, because you would put each statement on a separate line. You would indent. However, HOC does not force that. So in fact, the parser says j equals I times 2 and then print j. It knows that there's no way that that 2 and that print can go together. So that must be the end of the statement. So it recognizes this as 2 separate statements. So you as a person are, just need to accept, as somebody reading code, you may find things where it just looks like the one instruction ends and then the next one starts. And then, they may be on one line. It's weird, but it's a thing that you'll find as you're looking at it, but it's not a problem. It reads the way it has to read. There's only one interpretation that could be. So just do that interpretation. Just beware that you may come across it. Again, please don't ever write that yourself. Arithmetic operators. I mean, there's only one thing that anybody's going to use to represent addition, right? It's a plus symbol. Plus, minus, star for multiplication, divide, percent for modulus, all the same. HOC and Python. HOC doesn't have the integer division, so don't do the //. But regular plus, minus, star, division, modulus, exactly the same. You want to do a comparison operator. Well, what else is less than going to be? It's the less than symbol, right? All of that is the same in HOC and Python. Importantly, comparison, remember, obviously, is equality, 2 equal signs. Not 1 equal sign. If in Python you do an if statement with 1 equal sign, Python will yell at you. Will HOC yell at you? No. HOC will instead actually do a thing. And we'll talk about that later. If you see some logical operators, though, they're not the same. So you'll see this double ampersand thing. It's like and. Well, yeah, what does that mean? That means and. If you see 2 vertical bars, that means or. If you see an exclamation mark, just think not. If you know C or C++, those are the same as in C and C++. Again, Cunningham was involved with both. So these are the symbols. That's what they mean. HOC, one of the other things that you'll see, there's a lot more, in Python, we talk about true, we talk about false. You won't ever see this in HOC code, even if it's HOC code that's calling NEURON, because NEURON's perfectly happy responding true and false and things like that. You'll never see that in HOC. What you will see is the number 0 being used where we would say false in Python, and any old non-zero number being true, but HOC is not going to be that cruel to you. If you have a thing that's true, HOC will always return 1. All right, so is 4 less than 2? 0. It is not less than 2. Is 2 less than 4? 1. It is less than 4. I can do the or statement, compare, is 4 less than 2 or 2 less than 4? Well, yes, that's a 1. In Python, it would say true. but HOC doesn't have that concept, so it just says 1. What's the opposite of 4 being less than 2? Well, it's 1. By the way, secret thing that you may or may not know, in Python, you can actually use 0 and 1 for false and true almost always, but don't, because then you lose the semantic meaning, right? One little gotcha though, if you're trying to translate HOC in Python, HOC has this concept of fuzzy comparisons. If you see somewhere in the code a variable called float epsilon, that's setting the tolerance. How equal do things have to be equal? And so this allows you to deal with some fuzziness. And most of the time, this isn't going to cause you any trouble, right? Is 1 less than 1.01? Python and HOC by default are going to agree. Yes, 1 is less than 1.01. But in HOC, somebody might specify a different tolerance for what it is. So if I'm allowing if I set the float tolerance to be 0.1, so I'm allowing a fuzziness of 0.1, and I'll call anything within 0.1 equal, then 1 is no longer less than 1.01 because it's within the tolerance. 1 is instead equal to 1.01. Okay, well, nobody's going to set the error tolerance that high, so is that a thing that you ever have to worry about? Unfortunately, yes, because there's a slight gotcha here, because the error tolerance is not by default 0, it's 10 to the negative 11th. It's like 5 orders of magnitude larger than machine epsilon. So just because something compares equal in HOC doesn't mean it's going to compare equal in Python. So that's a potential gotcha that you have to look out for. They interpret comparisons differently.
Is there any way we can do that in Python? Like, can you have any float epsilon for Python?
I think you can, but I remember looking this up at one point. I think there is a way to do that, but I do not know what it is. Does anybody know off the top of their head? It's something obscure though. But
if you can do function overloading, I could see that maybe working, but I don't actually know that Python has that.
No, I don't know. I thought it was something buried. Well, I don't know. I can't find anything Googling real quick. But yeah, so if anybody finds anything, please go ahead and post on the Ask Tutors channel, because I think that's an interesting question. But yeah, so by default, Python equality, is literal equality and nothing but literal equality. By default, HOC equality has quite a bit of flexibility. So it's one little gotcha to be aware of. One other thing that you should know about, although it probably doesn't matter too much to you if you're just reading and not trying to write this, HOC uses rigid data types, by which I mean, Python's very fluid with data types, right? Something could be a string one moment and an integer another moment. Don't do that. That's bad practice, but it could be. In HOC, however, the first time that a variable gets a value assigned to it, it's going to be that one. It picks that data type, and it's going to be that data type for the entire duration of your program. So, and I guess also the related gotcha is that only doubles, so floating point numbers, can be use just sort of directly. So if I type x equals 2 in the HOC, it's perfectly happy. Everything else, though, has to be explicitly declared. And so the way that you'll find things explicitly declared, you'll see these str-def. I'm defining something to be a string, namely s in this case. And then you can assign s is equal to hello world. If you don't do that, str-def, HOC will yell at you. Objects, same thing. OBJRef is declaring something to be an object. So pi object. So then I can create a new object. So you don't just call it, you have to use this explicit new keyword to create a new thing. But that's what calls the constructor and all that jazz. So pi obj is equal to a new Python object. And again, this is kind of reminiscent of C++, if you know this. By the way, the other reason that I wanted to throw this out there, and I think I'll mention this again later, this basically gives you an object. This basically gives you an object that you could use pi.something to call a Python file, to call a Python function, much like you could use h.something to call a HOC function. More on that later. You'll notice here that x equals 2 in Python, that would be assigning an integer. HOC doesn't know anything about integers, just like it doesn't know anything about Booleans. Everything's a floating point number. Don't worry about it. Oh, also, by the way, these 2 slashes in Python, this would be integer division. That's obviously not what that's being used for here. 2 slashes means that everything after the 2 slashes is ignored. It's a comment. So it's basically equivalent to a Python £sign. So there you go. For 2 slashes 2 in Python is the number 2. For 2 slashes 2 in HOC is the number 4. Actually, that's a nasty one. So yeah, these 2 slashes are equivalent to Python's £sign. You can also see these slash star and star slashes. They're arbitrarily long. They can be anywhere. They can be in the middle of a statement. So a equals slash star. Please don't do this, but it's valid. HOC star slash 2 is equivalent to the statement a equals 2. Again, I'm not recommending that. However, I warn you that you may come across this. There's no direct equivalent to this star slash slash thing in Python, but you can use it, for example, similar to how you might use a triple quote at the beginning of a function to indicate what that function does, how it takes it, etc. This is a physics joke also. So in Python, everything is, whether or not a def thing that returns a value, doesn't return a value, nobody cares, because if you don't return a value explicitly with a return statement, it actually returns none, the none object. In HOC, these are separate concepts. So you have these things called procedures or procs. So you can have a proc, say fact, parentheses, and a proc never returns anything. It cannot return things. It would be wrong for it to do so. Versus functions or separate concepts, they must always return something. But the return statement, the return keyword works just like it does in Python. So this is a function that returns 1. And again, indentation doesn't matter, but you should use good indentation anyways. You call functions, open, close parentheses, no real surprises here. There's nothing in HOC that corresponds to namespaces. So basically your funcs and procs, they're either at the top level or they're defining methods. So here, for example, you see sign, S-I-N, but in Python, we would say probably math.sign. One thing that may come across is rather weird for you. So declaring things that don't take variables looks pretty much like it does in Python. Great. What about if they do take variables? Well, even if it does take a variable, you don't actually list the variables in HOC. you'll never see variables listed as function arguments. Instead, the variables are only ever referenced using positional indicators. So $1 refers to the first variable. $2 refers to the second variable. And so if you've ever done like bash scripting or something like that, you may have seen this kind of a syntax. What I would suggest is go ahead, you know, if you are going to, because you probably don't want to refer to, you know, again, you're not writing this, so it really doesn't matter. $1 is always going to be the first variable. If you're lucky, somebody somewhere gave these things meaningful names when they wrote the function. They may have created local variables and said X equals $1 and then referred solely to X inside the function. You can't, that would be what would happen if you were lucky. You can't count on that to be the case though. So in any case, the only thing that you can count on is any reference to $1 is the first thing. This is one index. There is no $0. $1 is the first thing, but only if it's a double. If it's a string that's been passed in, it would be an error for somebody to call $1. So you'll see, just like you'll see $1, you'll see $S1, which is the argument in position 1, assuming that it's a string. But if the argument in position 1 was an object, you'll see $O1. Or the argument in position 1 was a pointer. We've seen these like like underbar ref underbar t. You know, h dot underbar ref underbar t is a pointer. So pointers get accessed with $&1 would be the pointer that is in that was the first argument. It's not the first pointer, it's the first argument, and we're telling it that it's a pointer.
Oh, one doubt.
What's this?
If the first argument is a float and second argument is a string, would I say $1 and $S1 or $1?
Precisely.
Well, no. If the first argument's a float and the second argument's a string,
Or it's $S2.
and at $S2.
Yeah.
Okay. Okay, thanks.
So the number is always the literal position.
And there's a numarg that you can call, right?
Yeah, there's a numarg. There's like, I think also an ifarg to see if an argument exists. And I think there might even be functions to see what type it is. So there are ways to deal around with this and have some more flexibility. So this allowed people to build things that were kind of analogous to keyword arguments where there was some sort of a default value. Well, they didn't specify a second argument, so I'm going to assume the second argument is 5. But it's much cleaner in Python.
You probably won't run into that much.
But I'm pretty sure that does exist in ModelDB entries.
One more doubt. If there is a $1 and 2 specified inside the function, and if only if there are 3 variables, 3 parameters given, will there be an error? That
Nope.
That is not be no, right?
Nope, that just means that that third argument was ignored.
Yeah. Okay.
If, on the other hand, somebody accesses $2 and the function was called with 1 argument, then it'll yell, then it'll complain.
And can we give the default value to the second parameter, like $2 is equal to 5, can use inside the function? Just like that, even if they are not giving the second argument.
So no, but this is where the workaround with an ifarg comes in. I can post an example maybe on AskTutors, but I really would rather you, hopefully you're not going to write HOC. So hopefully it makes sense when you're reading it.
Yes.
Yeah. So there are all kinds of weird things that one can do, but if you follow it, it will literally make sense. It's just like, okay, sure. All right, but I mean, that's basically to work around, like I said, linguistic things. And so newer languages like Python have cleaner features. Again, all the more reason not to write it. One major gotcha in Python. Okay, so if you see, well, here's a HOC session. All right, so I have a variable called a, and I assign a to be 2, and I have a function, well, a procedure actually, because HOC makes a distinction between the two. I have a procedure that sets a to be 3, and I print out a. All right. So then surely, obviously, when I run this procedure, what it does is it prints out the number 3. A procedure says a equals 3, print a. However, by default, everything in HOC is global. This is the opposite assumption of everything in Python being local. So what that means is this, now that I've called the do a thing, it has changed the global variable a. A is no longer 2, a is now 3. So it's very easy in HOC to have functions that have side effects. This is generally considered a bad thing. You don't want your functions to have side effects. But again, you know, the Python that we know and love is decades removed from the creation of HOC and computer
If you
science.
want to assign multiple variables in a Python procedure, you'd have it return a tuple. If you wanted those new values to be accessible outside of the Python function, just have it return a tuple.
Yeah. Generally, globals today are considered things to avoid as much as possible.
Side effects. Stay away from side effects. Don't do it.
All right. So in Python, you have to explicitly declare something global to have it be global. In HOC, if it's again it's defaults to global and has to be explicitly declared to be local. It is just what it is. So you have to think about this and be wary, be on the eye, keep your eye out for any variables that are not explicitly declared as local, because they may be a sign of a function that's going to have a side effect. One other sort of gotcha that's going to come up if you're trying to interpret code, you'll see these references to so here there's a vector, it creates a new vector. Vector means the same thing as h dot vector. So this is an empty vector of size 100. And in Python, I'd have to say vec.size open close parentheses. Why is that? Because Python has functions. Functions are things, and you can do stuff with functions, right? Functions are first-class objects in Python. HOC is an older programming language. HOC didn't have the concept of assigning a function to a variable, right? Like that wasn't a thing when HOC was created. So if you just refer to a method, so vec.size, in Python, that would just be the method associated with this particular object. But in HOC, it says, well, I've got the method. I'm just going to assume that you meant to call it because that's the only thing that you could possibly have meant. So you'll see some code that should be calling a method. And in Python, we're used to thinking of it as a thing that needs open close parentheses. But you'll see some things that you're like, but that's the function name. Well, it is, but in HOC, if you're invoking a method can be invoked with or without the open close parentheses. So be careful, keep an eye out for that sort of thing. Again, if you're reading it, you see .size, you're probably, if all you're doing is reading it, you see .size, you're probably going to think, I bet it's looking for the size. And then you're golden. If, on the other hand, you're trying to translate something, don't translate it too literally. Don't see vec.size and keep it vec.size, right? Because then now that it's a function call. If you try and do it, you're going to end up as a problem. And you know, a little other sort of mildly annoying thing. This is a statement that this issue only applies to methods. It does not apply to functions. That is what it is. The other gotcha that I'm going to point out, and again, hopefully you never come across this because this is almost certainly a sign that somebody made a mistake when writing their HOC code. But if you have a single equal sign in HOC, a single equal sign is an assignment statement. All right. So A equals 1, B equals 2. If parentheses A single equals B, what that means is that B, the value of B gets assigned to A, and then it examines that value and decides if it's true or false using the rule. Remember that 0 is false and anything other than 0 is true. So if A equals B, that means that the value of 2 is assigned to the variable A. That's not 0. So then it's going to print out, it's going to go into the if block and it's going to print out A equals B, and the value of A will now be 2. Again, hopefully you never see this. Hopefully, you know, if you see a comparison, there's a double equal sign, but check, because somebody might have made a mistake. And in Python, that kind of a mistake would be a syntax error. There's this new colon equals thing, which is its own business. But in Python, this would be a syntax error. HOC is perfectly happy to let people do it. There are occasional reasons in Python. There are reasons why the colon equals exists in Python. It's occasionally useful. But like I said, most of the time, if you see this, you're going to have somebody has a bug. So you're going to really want to look into this to see what it is that they're trying to do and what they actually did. So keep an eye out for that. I guess that's less of a HOC to Python gotcha, is more of a somebody may have made a mistake when writing HOC. Relatedly, there's a bit of a syntactic flexibility here for an array. So if I have an array of doubles, so double x bracket 10, it's going to be a 10 doubles, floating point numbers. You know, you use the square bracket notation, x square bracket 3 is equal to 2, assigns to obviously the fourth element in that array because it starts out at 0. But the gotcha is that, remember, in HOC, once the type is declared, that's the type for all eternity until you turn off HOC. So if x is an array, then you could just say x, and well, what does it mean? But that's the array. What do I interpret that? How do I display that? Well, it's going to interpret that as the 0th item. You can assign to it. So even if you say x equals 5, right? Seems pretty clear. X is a double with a value of 5. No, it's not. If we had said that x was an array, x is an array for all eternity, and that assignment statement actually only assigns to the 0th element of the array. So you'll see this actually reasonably common. So the one example where this shows up almost always is in a netcon, and you'll see, remember, netcon weights are vectors. Well, they're arrays. Let's be correct. Netcon weights are arrays, but you'll see in c.weight equals 2 or something like that in HOC. What that actually means is it's assigning into the 0th element of the netcon weight array. So you got to watch out for that with HOC. There's this syntactic flexibility is potentially problematic. And fundamentally, the whole reason that we're talking about any of this is because HOC can be used to control NEURON, much like Python is. So basically, NEURON functions and classes, how do they work in HOC? How do you write in HOC? Generally speaking, you're going to drop the H. That's usually the answer. If it's a class, you know, so in Python, if I wanted a new vector, I would just say vec equals h dot vector. If it is a class thing, I do have to say a new to create an instance. But, you know, generally, you know, h dot cvode becomes just cvode. H dot I clamp becomes I clamp, and so forth. Almost always, the properties, the methods have the same names. There are some rare exceptions, and the only exception off of the top of my head, but I'm not willing to say it's the only one, is that for current clamp, current clamps have a variable called delay in Python. That's actually called DEL in HOC. The reason for this mismatch is historical, basically coming down to the HOC coming before Python, and that would be a syntax error in Python because DEL is a reserved keyword. I guess the other gotcha in Python, you would probably say, you know, if I created my CVODE object, CVOD equals h.cvode, then you'd say cvode.active true. But there is no true, so the corresponding thing in HOC is 1. Or cvode.active false becomes cvode.active 0. But generally speaking, there's a fairly direct translation from Python to HOC. Sections are, however, have special syntax because HOC treats sections at the syntactic level, right? So HOC is this, you know, I don't create an object that's a section. There's actually a special keyword called create that creates a section. So I can create a section called soma. I can create an array of dendrites going from 0 to 9, right? So that's 10 dendrites in total. And so here you don't have this business. There is no mismatch between, since everything is now done at the section, at the syntactic level, there's no longer any possibility of mismatch between, you don't have to explicitly declare the name. The name is the quote unquote variable name. It's not a variable. And so there's only one way of referencing it. So it is, I will say it is actually relatively clean in HOC to create sections. You could, if you're lucky, you'll find that people refer to them in the same way that they refer to it in Python. Certainly you can. Soma.diam is soma.length, which is 20. Cool. But in reality, you almost never do. Hate to tell you that. What instead happens in HOC is that HOC is this concept of the currently accessed section. And so if you know about stacks, this is actually construct a stack, and there's ways of sort of manipulating this. But what you'll see in this HOC is there's a special keyword called access. So if I access the soma, then my soma is now my currently accessed section, and I don't have to say soma.diam. I just say diam. And I know that the section that I'm talking about is whatever the currently accessed one is. And so if I use access, so what you'll see is access space something. And what we recommended, but not everybody did, but what we recommended in the days of people writing HOC, we recommended that you'd only do this once. You'd only make an access statement once. But people are free to write their own code. They'll write more than one access statement. And so then you have to figure out, in the context of the code, what was the last access section? There is, however, a way of syntactically avoiding this, which is actually relatively clever. So you can use curly braces. If you see somewhere where somebody said a section name and then curly braces, then those curly braces are declaring a block, and everything within that block refers to that section. And these can be nested, actually, which is kind of cool. And then the innermost section is the one that's active. But so everything inside of here, instead of saying soma.diam, soma.l, right? All of those things that are properties of the section, and only things that are properties of the section, are now, just assume that section by default. And this is true for both like variables, so properties like diameter and length, But this is also true for a whole bunch of methods that in Python rather would be section methods. So in Python, I would say soma.in3d open close parentheses to find out the number of 3D points. And in HOC, however, if I've accessed soma curly brackets, then you'll see in 3D living on its own as the number of 3D points. Oh, actually, I guess I had exactly that right here. So yeah, so that's the thing that you need to be on the lookout for. So you need to look at the sections that have curly braces. You need to look for access statements, because all of the things that in Python would be very explicit, what section are you referring to, can get very confusing tracking down in HOC, but you absolutely have to do that in order to try and understand something. The other major gotcha and the other major reason that this comes up is because HOC has no concept of segments per se. You never, ever, ever get a segment object, right? So I would say soma of 0.5 in Python to refer to the segment that contains the 0.5 location of the soma section. Can't do it, not a concept in HOC. And so what you see instead is you set the section in whatever way. By the way, if it's only one line, you can drop the curly braces. So soma of RVP dot begin parentheses 0 sets the section that we're talking about to be the soma, because Python has no concept, or sorry, HOC has no concept of soma as an object, so or segments for that matter. So this sets the section that we're talking about to be the soma, and then so instead of passing into my range of plot begin, remember range of plot shows the path between 2 points. Instead of passing into the range of plot that I want to start at soma of 0, which is what I'd say in Python, I set the section and then I just specify the X location. So anywhere that you'd see a segment in Python generally becomes an active section and an X location. And so then you've got to mentally invert this and convert this back into figure, wait, what segment am I talking about? So that's one of those things you have to be on the lookout for when you're trying to read HOC. HOC has this special syntax for connecting. It's a keyword, and so basically, if you see connect section 1 comma section 2, the first section is the child. It's what's connected to the parent. So just like connect den1 of 0 comma soma 1 means that the 0 location on den1 is going to be connected to the 1 location on the soma. This is equivalent in Python to saying den.connect soma, or den.connect soma 1 if we want to be explicit where on the parent we're connecting to. The gotcha, of course, is that there's this concept of a currently accessed section. So if the soma is accessed, then you'll find that people don't specify the section, and they may just specify a normalized location. What is the X value that declares the segment that you wish to connect to? So this is a thing that you may come across. And again, if you do come across connecting to a number, what does that mean? Well, it's just an X location, figure out which section is the active section. Again, the same rule applies for range variables. So in Python, we'd have, So in Python, I'd say soma of 0.5, I'd grab the segment, and then I'd say a property on the segment. HOC doesn't know about segments per se. So instead, the soma has voltage, let's say, or whatever mechanism, and that mechanism is at a particular location, a particular X value. So it'd be soma.v of 0.5. This is reasonably readable, right? It's the voltage on the soma at position 0.5. The place where this gets a little bit confusing is when there's a currently accessed section. So the section can again be separated from the V, which you'd never see in Python. So if you see V of a location, that's referring to whatever the currently accessed section is. The variable reference. So in Python, you'd grab a mechanism and then you get the mechanism's value. In HOC, you'll see it in the reverse order. It's just the way it is. So if I want to know the value of the M variable that belongs to the HH mechanism, so in Python, we're just sort of scoping down, right? SOMA is the whole section, SOMA of 0.5 is the segment, SOMA of 0.5 Hodgkin-Huxley mechanism, and then the M gating variable with respect to that. All right.
Yeah, this follows kind of naturally from the old mathematical notation. When one saw printouts of the equations and the parameters that were used in computational neuroscience modeling papers or textbooks, one would see the name of a variable and a subscript. Okay, so it'd be M subscript HH, and the underscore between the M and the HH was kind of a crude typewriter reminder to the reader that the HH is actually supposed to be a subscript. And that's why you also, well, anyway, so this is why this notation that HOC used seemed more natural to people, because what they were used to seeing was these formulas in which the name of the mechanism was a subscript. So it might be M for a sodium channel, it might be M underscore Na. For a potassium channel, it would be N underscore K. And so everybody was used to seeing subscripts in a mathematical formatted printed page in an article, hence this notation. That's how best to think about it and understand it now when you're looking back at this stuff from the perspective of Python.
Yeah, that makes a lot of sense. And so this is more of a programming style where we're scoping down to grab our item.
And it's perfect object-oriented notation. It's what comes naturally in an object-oriented modeling environment. But Neuron actually started out without any idea about objects at all. It was nothing. It was like a glorified BASIC, practically, with C syntax.
So. And so I will. Two things. Again, remember, nobody's saying that the SOMA is going to be mentioned when you see M underscore HH, because you may see these mechanisms referred to without the section, because the section might have been specified somewhere, God knows where else in your code, and it becomes the currently accessed section. So you'll see that all the time. You'll just see M underscore HH of 0.5.
Yeah, so if you ever have to take old HOC code and re-implement something in Python that borrows from it a little bit, and you're not sure what's being referred to, put in a print statement close to this assignment, like if it says MHH equals whatever, put in a print statement right there and say print sec name, or just sec name. And that'll tell you what is the default section's name at that point where the code is being executed. And that's how you can discover the stuff if you ever have to actually re-implement stuff in Python.
That's good advice. Oh, the one other thing that I will mention, just because you may see it elsewhere and we've not acknowledged that this exists, you could also in Python does support the underscore notation, but not in quite this format. So you could also see SOMA of 0.5 has to be grabbing the section, but .m underscore HH. That will also work in Python, but I don't think it's as natural in the object-oriented context. So I would stay away from it, but you may see it. All right, pointers. So we know in Python we use underbar ref underbar to grab something, grab a pointer. In HOC, you use the ampersand. You know, so if I want to record Membrane potential, it's going to be the ampersand, the address of, it's a thing carryover from C. V of 0.5 is going to be the recording a pointer to the membrane potential at the center of whatever happens to be my currently accessed section, which in this case is soma, way up here. So this is equivalent to this underscore ref business that we've been using before. So I want to point this out though too. If you do find yourself needing, occasionally you're going to need to call HOC code that you expects pointers. So the way that you do this in Python, if you have something and you want to send a pointer and it doesn't already exist, you can use what's an h.ref to create the relevant reference. So var1 is h.ref of 42, creates a pointer to the number 42. It's going to reserve some memory for the number 42, and then it's going to create a pointer to that. And then you can use this in any HOC function or neuron function that would expect a pointer normally to a double. If you want a pointer to a string, we'll just create an h.ref to a string. If you want a pointer to a list, create an h.ref to a list. And we have to do this because Python doesn't support pointers directly for good reasons that you can look up online if you're curious. And so these, once you have these references can be used just like any other pointers that you create using underbar ref underbar, you know, so their value is square bracket 0 and you can assign to the square bracket 0. Yeah.
Now, question for you here. If you're making assignments to these variables, the var1, you could say var1 equals 16. And now the value stored in that memory location will be 16. Is that correct?
Yes. So what's happening is two things are happening, which I think may address your question. First of all, it's allocating memory to store the variable 16. And second of all, it's storing also a pointer to that memory location.
Okay. What if you want to change this string, which is referred to? Can you simply do a print to a, can you simply take another string and assign that to var2, or do you have to be worried about whether, good, so it's flexible. It doesn't have to have the same length as the original string.
That is correct.
Okay.
So yeah, so this ties into this is an important thing to point out. In Python, strings are what's known as immutable. A string is a string and cannot be changed. So this is a workaround for any HOC functions that want to change a string, which is a thing that people have written. I wouldn't, but it's a thing that people have written because it's a, I wouldn't do it because it's a side effect. I'd return a new string, but there exist functions that change strings. And so this is how you can work with those.
Yeah, you don't want to be doing that much, really. Yeah.
There's at least one example within the built-in neuron functions that does that. But I'm gonna skip this for the most part. I'm just gonna point out that if you see iterators, if you ever see the word iterator, go back to this slide. But basically, they are the equivalent of what's known as a generator in Python. And so there's this thing called iterator statement, which I don't know why on earth anybody would, why that's the name. But it's basically the equivalent of a yield in Python. And so this is a strategy that lets you do something very similar. So this is a strategy that will let you do something very similar to a for each, or, you know, in Python, a regular for when you're looping over an item over a bunch of things. So here with this code, X will take the values 1, 2, 4, 7, and -25 in that order. That's a thing that you'll find in some examples in Model DB. I think I took this example directly from Mod. Well, maybe not.
In Python, the natural thing would be to just make a list and iterate over the list, right?
Yeah, in Python, all of this collapses down into for X in square brackets 1, 2, 4, 7, -25, print X.
Yep.
But if you
God.
yeah, if you see iterators, go back to this slide. You'll have these slides. I'll post this in a little bit. I do want, we are over time, and I want to be respectful and come to an end as quickly as possible. So we've already mentioned sec name. We'll tell you the current section. So for all is a thing that you can use in the context of something that people use in the context of a where you might use a section name, except instead for all loops over every single section name, loops over every single section. So that's roughly equivalent to for sec in h.allsec. There's also for sec and then that takes a list of sections. In HOC, those lists have to be special objects. They can't be arbitrary objects. There's a special object called section list. You don't care because you're just reading, you're not writing. But so if you see for sec in my section list, think of it as equivalent of first sec in my section list, colon, boom. And then the other thing that I want to point out is that you'll see these sort of regular expression on some rare cases, for sec and then a string that applies regular expression that loops over everything and only runs it for those strings, for those sections whose name matches a certain regular expression pattern. There's no direct equivalent in Python, but you could literally do what I described for sec and h.allsec and then check for the regular expression patterns. You'll see if we want to do segments, again, we've already said segments don't really exist in HOC. So instead, you'll see the syntax of for parentheses x comma 0 is going to loop over all of the centers of the segments. And so x will take the values. So if I have 5 compartments, then this is going to go 0.1, 0.3, 0.5, 0.7, 0.9, because those are the centers of those segment locations. Cool. A little thing to be aware of, this comma 0 flag may seem a little odd, and it is. And honestly, so this is equivalent to a thing called sec.allseg, but you'll notice that we almost never do, we always say for seg and sec, we don't say for seg and sec.allseg. And the reason being is because if I didn't have that comma 0 there, I would also hit the 0 and 1 points, which have voltage values, but do not have concentrations. If you set based on the 0 and 1 locations, it will do the wrong thing because it will set a point twice.
And they don't have currents either, do they?
No, just voltages, I think. So you may come across for x parentheses, paren x. Well, I mean, probably not paren x, but if you may come across for x parentheses, and that would hit all of the segment centers and the 0 and 1 locations. So it's a different behavior. It corresponds to allseg. But if you find that, check it out and see if you actually want to hit the 0 and 1 locations, because I would guess more often than not, you don't.
You will see sometimes people implementing variation of parameters with distance along the length of sections, and some very widely reused model entries make the mistake of iterating over all seg. So they start out and they try to do something to channel density at 0, and that gets overwritten by channel density at the next node, which is fine. But when they get to the last node, then they hit that one twice, and it ends up with an incorrect value. I'm not going to mention any names, but
yeah, so just don't, and be on the lookout for it. And then if you see a empty for x, think about whether or not that's what you want to do. And then if you decide that is what you want to do, think about whether or not that's what you want to do again. One other thing that I want to throw out here, you'll see sometimes some functions take strings. So HOC strings will be embedded in these functions. But basically that just means that this is what's known as a callback. This is whenever this function gets invoked, and this has to do with initialization. We'll talk about initialization on Tuesday. It runs this code on a net, right? So the equivalent in Python is just to pass in the function handle. You don't, no open close parentheses, because I'd be running it. No string, just the function. So that's the mapping between the two. Basically, if you see a template in HOC, think class, and pretty much you'll be fine. Yeah, okay, and just to touch on this very briefly, Python and HOC are perfectly happy talking to each other. You can load any HOC libraries. We've been doing this all this time. We've been loading stdrun.hoc, for example, with an h.load file from Python. That's also true if you have something that your lab's developed. h.load file, my labs thing, .hoc. Cool. And then any function that's declared inside there, just like continue run is declared inside std run. Any function that's declared inside that loaded file, you just put an h dot and it will probably work with all the caveats that we've discussed otherwise. If for some inexplicable reason you want to execute HOC literally from within Python, you can pass it as a string to the H object itself. And so this would declare in HOC, this runs the HOC command that declares this function, and then you could pass in, you could call that function from Python by putting an H in front of it. So in HOC, this would be hello. In Python, this becomes h.hello, and then you pass in world, and then it's going to say hello world. Again, this is one of those things where if you find yourself wanting to do it, think about that, whether or not you want to do it. If you decided that you do, think about it one more time before you actually do. Because there's probably no reason to do it, but the point is that you can. The one, I think this is the last slide. If it's not, it's almost the last slide. I just want to point out that HOC is not the same thing as NEURON, right? In NEURON, in Python, we're very used to getting data types, right? So if I do a v.size, where v is a vector, what's my vector.size? I'm going to get an integer back. If I have that size, even if I call that function from within HOC, that in HOC is a double. And if that number dot size ever touches HOC, then it has to be a data type that HOC knows about. So while v.size is going to return an integer, if I have nothing but a HOC function that grabs the vector.size and returns that value, it's going to come back in as a data type that HOC knows about, which is a float. Same thing for anything that returns a Boolean, right? If it returns a true false in Python, if it touches HOC at all in the process, it's not going to be true false. It's going to be whatever, whatever you started with, whatever HOC knows about. So it's going to be 0 or 1. And that's the identity example. So HOC and NEURON are not the same thing. They're both different. HOC and Python are different layers of talking to NEURON. And so you're better off, so you'll get the data types, you'll get everything that you expect if you talk to NEURON directly rather than going through from Python. I already sort of mentioned this. If I want to run a Python command, I can use enter in Python from the HOC side. This is how HOC could call Python. If I want to call a Python function, I do this PyObject bit, create a PyObject thing. And then so now since I've imported math, then PyObject.math is the Python math thing. And so it has an arc hyperbolic cosine. And I can see what the arc hyperbolic cosine of 2 is from HOC. All right. And with that, I do apologize for this running long, but that is my last slide. I do want to say, well, I guess I can ask if anybody has any questions on any of this. And if not, here's your exercise. I will post this on the Slack momentarily. Here is a HOC function. Here's a HOC command. And what this does, well, I will show you this because this won't take long. But what this does is this creates a graphical interface where you can specify parameters and you can have it do a couple of things. So what I would like to suggest, and so you can see it, here's some HOC. I would like to suggest that you try to take this exercise code, which was written in HOC, and see if you could do the same thing in Python. And the reason that I'm wanting to do this, again, you never, ever, ever have to translate from HOC to Python. But we haven't talked about how to write graphical interfaces. I'm not going to talk about how to write graphical interfaces. Maybe I'll make some in a subsequent video in some future date. But you know, you can find examples of things that are in HOC, and can you use them? Can you read it enough to figure out how to do the same thing in Python? And then if you can do this, you could just as easily make a function that gave you a version that gave you a button that you could press for running a Hodgkin-Huxley simulation versus a Hodgkin-Huxley simulation, but now with double the leak conductance. I don't know. Right? You could make interfaces, and if you make interfaces, you can share these interfaces with people that may not be happy working with code. So there's a reason for doing that as well. But again, really just, you know, to what extent can we understand, from an understanding of how to read HOC, can we actually figure out how to do this? And so, well, okay, so just final thing. Where is this? It is over here. And so what I have here is, if I were to run this, I would say enter in GUI exercise.hoc. It's going to pop up the GUI main menu, and it's on another screen. I apologize for that, but it creates this field where I can enter a thing, and then I have these two buttons, a do count and a do half count. And if I set t-stop to, let's say, 7, and it does do count, it goes 0, 1, 2, 3 through 6. And do half count goes 0, 1, 2, 3, blah, blah, blah to 6.5. Oh, by the way, this is the other thing that you should do if you're trying to translate, trying to understand HOC. Run it. See what it does. Like, it's good to read it, but, you know, run it. See if it does what you think it does, because that's going to give you some hints too. So think about it. And with that, again, I'll do one final call for questions. Thank you so much for sticking around. I know we ran over. Questions? And if not, I'll see you guys on Tuesday, and I hope you have a wonderful weekend.